My name is Chandrasekhar. I am a student in CMRIT, Bangalore, India. I am here to present my research background on design and analysis for the presence of bacillus cereus and blood using plasmodes. Abstract. Biosensors are based on refractive index detection. Design of 2D layer sensing structure is done using SPR technology, that is surface plasmon resonance technology. The photonic waveguide biosensor use plasmodes for detection and analysis of bacillus cereus. FTDT is used in designing the sensor. Wavelength and frequency spectrum are calculated using RSOFT simulation tool and OPTIFDTD tool. A slight variation in refractive index leads to a substantial change in the frequency which can be seen in the band structure. Therefore, the design structure behaves as sensor. Objective: to design and test a sensor that can detect the presence of bacillus cereus and blood using plasmodes with higher sensitivity. The SPR optical sensor built on a metal dielectric configuration which is used for the detection. A silver or gold configuration is used as a sensing material to detect the analyte to attain decent chemical resistance by keeping sensitivity high. That is, the gold or silver layer should be used to increase the sensitivity. Finite arrangement for spectral surface plasmon resonance sensor must be 2 nanometer for gold and 48 nanometer for silver dielectric. Working principle: as we can see, the optical transducer is being placed. On top of it, the analyte, that is bacillus cereus, should be placed. Then the light source is being incident to the analyte. When the light is being incident, the plasmodes will be created. These plasmodes will be detected using the monitor, that is the detector at the output will be placed. By using these plasmodes, the various graphs such as frequency spectrum, transmission spectrum will be plotted. So this is how the basic biosensor will work. Working principle: when monochromatic light, polarized light, strikes the interface of two media, the light is partially reflected. In SPR, the prism is covered with a gold film. The free conduction electrons in gold produces periodic oscillation which is called plasma waves. The proposed design is a SOI-based surface plasmonic resonance biosensor which is based on interferometer, where metal dielectric interface at the input port acts as a source for plasmon polaritons whose impulsive responses are subjected to variation in the effective refractive index. The proposed structure using RSOFT is being shown in the waveguide sensor design. The first layer, that is the bottom layer, which can be seen is the zinc silicon dioxide. On top of it, the brown color, that is silicon dioxide, is being placed. On top of it, titanium oxide is being placed. And the gold layer, that is yellow color, is being embedded into the titanium oxide layer. This forms the sensor structure. The blue colored layer, that is the water, and the analyte, that is dark blue colored layer, is being placed on top of the sensor. As we can see, a small light is being passed, light source is being passed through the titanium oxide. Here, the light will be passed and a monitor is being placed at the top, as we can see, the green color one. When the light is being passed through, the monitor will detect the plasmodes as told earlier. So this is the proposed structure using RSOFT. The simulation flowchart, how it works in RSOFT. The basic starting steps in RSOFT are define material properties, waveguide profile, initial simulation, domain properties. Provide light wavelength source. Then the design file which is being generated will be in the form of .ind format. In order to perform simulation, define field excitation. That is, we have to select the transverse electric or transverse magnetic excitation source, whichever is being required. As per our requirement, transverse magnetic wave is being selected. Refractive index changes of analyte changes in the transmission or reflection. Using these scenarios, the graph will be plotted. The proposed structure using OPTIFDTD can also be seen. the same design which I had told in RSOFT is being replicated using the OPTIFDTD software. In this software, 2D refractive index, 3D refractive index, power spectrum analysis, transmission spectrum analysis is being noted down. This is the design description. The waveguide layer, their respective refractive index and their thickness. Silicon dioxide has the refractive index of 1.45 and the thickness considered is 0.101. This thickness are based upon the literature survey and our research values. Zinc silicon dioxide refractive index is 2.198 and the thickness is 0.22. The water refractive index is 1.33 and the thickness is 5. And for gold it is 0.74 and thickness is 0.074. For titanium dioxide it is 2.62 and the thickness is 1. The sensor design. The structure design includes segments of waveguides. This waveguides includes metals that has the capacity to absorb the light, that is the source. The incident light is absorbed by the electrons in the metal to constitute the storage. These segments are laid parallel to each other. A monitor, that is spectrum analyzer, is placed at the end of the waveguide to capture the reflected waveforms. The OPTIFDTD software is also being used to obtain the 3D modeling of the design. In this software, the refractive index of the design is used for the simulation. The gold is being used as a sensing layer of the design. The bacillus series is the solution which will be placed on top of the optical sensor top layer. The sensing layer reacts with the solution to form the plasmons. These plasmons are absorbed by the observation point. As refractive index of biosample taken into consideration will change according to different concentration in water, this shifts transmission frequencies and transmitted output power layer which may be absorbed from the transmission spectrum. Frequency graph. This figure is being obtained by the RSOFT software. This is the wavelength response with respect to the amplitude of two monitors, where one monitor kept above the metal dielectric interface and one kept below the metal dielectric interface. The responses from the monitors when compared shows shift in the wavelength of 0.02 micrometer, which is slight change in the wavelength. The simulation results obtained in RSOFT. As told earlier, the light confinement can be seen through the titanium dioxide layer and the gold is being embedded and the monitor is being placed at the top. The gold is being considered here because the silver gets oxidized with respect to time. Hence the silver has the disadvantage. Therefore gold is preferred over silver. Simulation results in OPTIFDTD. This is the transmission response in OPTIFDTD, that is the dip which we can see, which is been obtained for the bacillus series cell. So this is the data which can be stored, and for all the bacillus series in blood will have the same data value. Whenever this is being compared, we can prove that the bacillus series in blood is present. Parameters calculated here are sensitivity, that is the sensitivity of the sensor is being calculated. It is given by the shift in the resonance wavelength to change in the refractive index of the analyte. So most analysis is performed using RSOFT, that is the two test values are being generated and the change in the analyte value with respect to change in the frequency shift will be used to measure the sensitivity of the sensor. Conclusion. The surface plasmon resonance is the most widely adopted technique to analyze the biomolecular interactions and also detecting the components of the interest present in the sample over the metal surface in real time. The sensitivity of the design sensor has been calculated and found to be 105.565 nanometer per RIU. The analysis is carried out by varying refractive index, which resulted in the proper functioning of device by producing the shift in the wavelength, thus making the proposed design compact and relatively easy. These are the references which have referred. Thank you.